Eddy current testing is an electromagnetic testing technique that has many advantages over other methods for inspecting thin conductive materials. Perhaps going forward, instead of repeatedly saying eddy current testing, I will simply say eddy current. I'm sure you will appreciate this truncation in the long run. That being said, eddy current is a versatile technique that can be used not only for flaw detection, but can also be used to perform various material assessments related to conductivity, permeability, or dimensional characteristics. Eddy current is very sensitive to small discontinuities at or near the test part surface. Eddy current also provides immediate results that are ready to evaluate. Eddy current instruments are very portable, and minimal test object surface preparation, if any, is required. As you well know, there are pros and cons to nearly every situation, and the eddy current technique is no exception. In order to be inspected using the eddy current technique, materials must be electrically conductive, and eddy current testing has a limited inspection depth, normally around 1/4 inch or so for non-ferromagnetic materials. For ferromagnetic materials, the inspection is normally limited to the surface. Eddy currents are also very sensitive to permeability changes in the material, which can negatively affect flaw detection and data interpretation. Discontinuities oriented parallel to the test coil windings, such as laminations in plate when using a surface pancake coil, may go undetected, which is why coil design and orientation is critical to detect certain types and orientations of discontinuities. Reference standards are also needed for instrument calibration and setup. The large number of potentially significant variables in eddy current testing is both a strength and a weakness of the technique, since effects of otherwise trivial parameters can mask important information or be misinterpreted. Virtually everything that affects eddy current flow or otherwise influences test coil impedance must be considered to obtain reliable results. Thus, credible eddy current testing requires a high level of operator training and awareness. Eddy current testing results are sometimes psychologically difficult for component owners and operators to accept. For example, radiographs provide images of flaws. Similarly, liquid penetrant or magnetic particle inspections provide evidence of a discontinuity in the form of dye penetrant leaking out of a discontinuity, or iron filings lining up at a flux leakage point. Eddy current tests are reference-based tests, meaning that the data evaluator is comparing signals, often referred to by non-qualified bystanders as squiggly lines, from calibration standard flaws to the signals produced during the actual testing of the component. Therefore, it is not uncommon for an owner or operator of a component to challenge the results of an eddy current test, especially when costly unexpected material degradation is reported. For this reason, it is necessary to back up your results with measures such as performing retests if data quality is questionable, or testing the material or component using a confirmatory technique, such as a rotating coil or array probe technique. Forensic material examinations can also be used to confirm suspected degradation. Electromagnetic testing, or ET, is one of the oldest non-destructive testing methods, with early investigations of ET principles dating back to around 600 BC. Around that time, Thales of Miletus, a Greek philosopher, observed that a lodestone, a naturally occurring magnetic mineral, had the ability to attract other objects made of iron. Around the turn of the 13th century, magnetic compasses were being used for navigation purposes. Around 400 BC, Democritus, another Greek philosopher, provided his formulation of atomic theory. which describes all matter in terms of atoms and their properties. In the 1820s, Danish scientist Hans Christian Ørsted discovered the link between electricity and magnetism, and that electric current flowing through a conductor causes a magnetic field to develop around that conductor. Ørsted also observed that winding a wire into a loop or coil intensifies and changes the shape of the magnetic flux field around the wire and coil. Ørsted also observed that winding a wire into a loop or coil intensifies and changes the shape of the magnetic flux field around the wire and coil. Ampere discovered that two currents running opposite directions in two close-together conductors would cancel out the magnetic field. Two current-carrying conductors, with some distance between them, each have an associated magnetic field which flows around the conductor. But when the conductors are placed adjacent to one another, as shown on the right, the magnetic fields are cancelled. Also, that the magnetic field direction changes when the direction of the direct current changes. In 1824, French physicist François Arago observed the following interactions between a magnet and a conductor. The oscillation of a magnet was rapidly damped or slowed down when a non-magnetic conductor was placed underneath the swinging magnet. Arago also observed eddy currents in 1824. Arago also noticed the interactions between a magnet and a non-magnetic conductive disk. By rotating the disk, the magnet would follow the rotation of the disk. Arago took a magnetized needle and affixed it to the end of a string. He then attached the string to a hook and placed a stationary electrically conductive disk directly underneath the stationary magnetized needle. Arago then slowly rotated the conductive disk, and lo and behold, the magnetized needle would start to follow the rotation of the disk. Surely Arago wondered what mysterious forces were causing the needle to follow the disk. In the mid-1800s, French physicist Léon Foucault was also heavily involved with the research of electromagnetism and eddy currents. Because of Foucault's work, eddy currents are sometimes referred to as courants de Foucault, which translates to Foucault's currents. In 1831, English scientist Michael Faraday was credited with discovering electromagnetic induction, which is the basis for the electromagnetic testing method. Faraday's law of induction says that when a magnetic field changes, it causes a voltage, a difference in the electric potential that can make electric current flow. Movement of a magnet through a coil induces a momentary measurable current in a coil. For current to be induced in a conductor by means of electromagnetic induction, the magnetic field must be moving or alternating. Faraday attached a coil to a galvanometer, a sensitive device used to detect electrical current, to a coil. He then moved a bar magnet down through the coil and noticed that the needle on the galvanometer would move. The needle would reflect to the left when the magnet entered the coil and would reflect to the right when the magnet exited the bottom of the coil. When the magnet was inverted from its initial orientation and inserted through the coil, the needle deflected to the opposite side of the meter. This highlights an important point, that the opposite ends of a magnet have different polarities. Magnetic polarity will be discussed in a future module. I appreciate your patience. In 1834, Russian physicist Emil Lenz observed that an induced current produced by a varying magnetic field will flow in such a way that the induced current will create its own magnetic field that opposes the magnetic field that created it. Lenz's law. According to Lenz's law, when the north pole of a magnet is approaching a coil or moving relative to another conductor, the induced current flows in such a way as to make the side of the coil or conductor nearest the pole of the magnet itself, a north pole, to oppose the approaching bar magnet. Each time the magnet approaches the conductive plate, eddy currents are produced in the plate, and those eddy currents produce a magnetic field that opposes the magnetic field of the approaching magnet. Perhaps when you were a wee child, your mum let you play with magnets. If you had the occasion to place the north pole ends of two magnets near each other, they would repel rather than attract the other magnet. This was likely the first manifestation of Lenz's law in your life. Another way to demonstrate the effects of Lenz's law is to drop a magnet through a copper tube. The falling moving magnet creates eddy currents in the tube wall. As per Lenz's law, each pole of the approaching magnet is opposed by the like polarity pole produced by the eddy currents, causing electromagnetic drag. This electromagnetic drag is the basis for eddy current braking, which is used for many different applications, including bringing roller coasters and high-speed trains to a slow, smooth stop without friction, stopping the rotation of an electric drill after the trigger is released, and used in fitness applications such as rowing machines and elliptical stair-steppers to increase resistance. It should be noted that the changing magnetic field can be produced by any of the following methods: moving the actual magnet relative to the conductor, moving the conductor relative to a magnet, or by creating an alternating, changing magnetic field by energizing the test coil with alternating current. In the late 1870s, Scottish scientist James Clerk Maxwell created a remarkable two-volume work titled A Treatise of Electricity and Magnetism, which provides the basis for current-day knowledge of electromagnetic theory. Friedrich Bessel, 1784 to 1846, was a German mathematician that made significant contributions to engineering, providing solutions to differential equations used in physics and engineering. Dr. Frederick Forster used Bessel functions in his work on his similarity laws to develop characterization of coil responses to changes in test material properties. Imagine grasping the conductor with your right hand, with your thumb pointing in the direction of the direct current. Your four other fingers, if you still have all four, would be pointing around the conductor in the direction of the magnetic field. This is called the right-hand rule, and is a handy way to remember the direction of magnetic field orientation relative to current direction. If direct, non-alternating current is flowing through a primary conductor and a secondary conductor is placed stationary near the primary conductor, no current is produced in the secondary conductor and no opposing magnetic field is created. Hopefully you remember that if there is no motion, there is no induced current. However, if direct current is flowing through a primary conductor and a secondary conductor is constantly moving relative to the primary conductor, eddy currents will be produced in the secondary conductor, which will produce an opposing secondary magnetic field. If an oscillator is used to energize the primary conductor with alternating current, the primary magnetic field will be an alternating magnetic field, which will induce alternating currents, called eddy currents, in the secondary circuit. The alternating current induced in the secondary conductor will then produce its own magnetic field, referred to as the secondary magnetic field. The secondary magnetic field is smaller than the primary magnetic field and is always in opposition to the primary magnetic field. As the current alternates, so do the primary and secondary magnetic fields. The opposing magnetic fields change direction twice per cycle of alternating current. The magnetic lines of force are most concentrated near the center of the coil and become less dense as lateral distance away from the coil increases. To generate eddy currents in a test object, first we have to energize the coil with alternating current. Very soon after the test coil is energized, we arrive at step 2, which is the development of the primary magnetic field through and around the test coil. Notice how there are no eddy currents present and no secondary opposing magnetic field. Hold your horses. That doesn't happen until the coil is placed near a conductive material. At step 3, the test coil is placed near the conductive material, and the alternating primary magnetic field starts to interact with the test material. At step 4, the alternating primary magnetic field starts to introduce eddy currents in the test object by electromagnetic induction. We finally arrive at step 5, where eddy currents are producing their own magnetic field, called the secondary magnetic field, that opposes and therefore weakens the primary magnetic field produced by the coil's alternating current. By the way, eddy currents are doing a lot of hard work in the material, and they lose some of their energy in the form of heat. Due to improvements in computing ability and computer software/systems, there have been many developments in eddy current testing in recent years. Probe development has also advanced, using more array probe technology in recent years that greatly increases the speed of inspections and provides more information than standard coils. Eddy current testing is now a widely used and well understood inspection technique for flaw detection, as well as for thickness testing, conductivity testing, and more. Some historical, and even some current, technical and training materials refer to eddy current coils as transducers. A transducer is simply a device that converts variations in a physical quantity, such as pressure, magnetic field changes, etc., into an electrical signal, or vice versa. Even though an eddy current coil fits the description of a transducer, eddy current test coils are more often referred to as coils rather than transducers, although either definition is correct. Going forward in this training program, eddy current coils will be the term used. Numerous electromagnetic induction or eddy current comparators were patented in the United States from 1925 until the end of World War II in 1945. Rapid technological developments in many fields before and during World War II, from 1939 to 1945, contributed both to demand for non-destructive testing and to the development of advanced test methods. Eddy current testing rapidly developed, particularly in the period of 1950 to 1965, when Dr. Friedrich Forster, a German professor, developed sophisticated electromagnetic testing equipment. Dr. Forster has been endearingly referred to as the father of modern eddy current testing due to his pioneering work in the field. Dr. Forster's development of the law of similarity and associated impedance graphs were groundbreaking in terms of understanding the relationships between material properties and their effect on test coil impedance. Eddy current testing started becoming much more prevalent in the 1970s as industries realized how well this non-destructive test method was suited for various applications, such as in the nuclear, automotive, petrochemical, and aviation industries, just to name a few. For many applications, eddy current testing is a fast, cost-effective way to examine certain materials and products, and offers good sensitivity to small discontinuities. Due to the rapid improvements in technology in recent decades, test instruments have gotten smaller and much more powerful than instruments used in the past. Many advancements have also been made in array probe technology in recent years. Eddy current array, or ECA, probes can contain a single band or multiple bands of individual coils. allowing substantially more coverage in a single pass than when conventional single-coil probes are used. Eddy current array probes effectively eliminate the time-consuming raster scanning necessary when pencil probes are used, which has a significant impact on inspection speeds. Probe delivery systems have also improved in recent years. Robotic probe delivery systems and increasing scanning speeds have drastically reduced the time it takes to inspect large components, such as tubing inspections in large heat exchangers. Inspections that used to take weeks using older probe delivery systems and instrumentation can now be completed in just a few days. Pairing robotic probe delivery systems with array probe technology has even more efficiency. For example, manual eddy current inspection of large aircraft wheels using pencil probes can take several hours. Robotic fixtures using eddy current array probes can complete the same wheel inspection in a matter of minutes, with improved accuracy. The American Society for Non-Destructive Testing, or ASNT, is a technical society for non-destructive testing professionals. ASNT performs many functions in the world of non-destructive testing, and one of its main functions is to help companies ensure that their NDT employees are properly trained so they can safely and effectively perform their jobs as NDT inspectors. ASNT has developed and published various standards and recommended practice documents to help NDT employers ensure that their NDT employees are properly qualified and certified. Two of the main documents ASNT has developed/published for those purposes are Recommended Practice Number SNTTC1, Personnel Qualification and Certification in Non-Destructive Testing, and ANSI ASNTCP 189, ASNT Standard for Qualification and Certification of Non-Destructive Testing Personnel. The most fundamental difference between the two documents is that CP 189 is a standard that details minimum requirements, while SNTTC 1 is a set of recommendations for an employer-based training program. There are other organizations besides ASNT that provide similar recommendations and requirements for NDT training and certification programs, depending on the specific industry sector, regulating organization, etc. For the purpose of this training, the focus will be on the qualification levels provided in the ASNT documents. Three basic levels of qualification that follow SNTTC1 or CP189 are Level 1, Level 2, and Level 3. An individual in the process of becoming qualified or certified to Level 1 is considered a trainee. Level 1 personnel may perform specific calibrations and non-destructive tests in accordance with specific written instructions and record test results. Level 1 personnel may also perform NDT job activities in accordance with written instructions or under direct supervision from Level 2 or Level 3 personnel. Level 1 certified individuals are not qualified to interpret test results. Level 2 personnel may set up and calibrate equipment and interpret and evaluate results with respect to applicable codes, standards, and specifications. Level 2 personnel may also organize and report the results of non-destructive tests. Level 2s exercise assigned responsibility for on-the-job training and guidance of Level 1 and trainee personnel. Level 2s must be thoroughly familiar with the scope and limitations of each method for which the individual is certified. Level 3s develop, qualify, and approve procedures, and interpret and evaluate test results in terms of applicable codes, standards, specifications, and procedures. Level 3s assist in establishing acceptance criteria when none are available, and are responsible for certification, training, and examination of Level 1 and Level 2 personnel. Electromagnetic testing, or simply ET, is one of the main recognized ASNT non-destructive test methods. The electromagnetic testing method encompasses three distinct techniques, including remote field testing, or RFT, alternating current field measurement, or ACFM, and eddy current testing, or ECT. The three electromagnetic techniques listed above are all based on the principles of electromagnetic induction. Any eddy current testing system requires the following basic components: a generator or an oscillator to generate the alternating current supplied to the test coil, a test coil, and an indicating device, such as a meter or an oscilloscope. Many eddy current instruments are standalone, meaning they have their own display and require no other equipment to perform the test, other than the test coil. Some of the more complex eddy current instruments may need to be interfaced with a computer and monitor to perform setups, acquire and record data, review data, etc. Many modern instruments have Bluetooth and network capabilities as well. This slide shows the basics of an eddy current test system, but don't be fooled by the simplicity of the slide. Eddy current instruments are highly specialized, and with the right test coil and proper calibration, can be used to find very small discontinuities in thin conductive materials. The goal of this training course is to teach the fundamentals of eddy current testing. The scale in many of the illustrations is purposely oversimplified to draw attention to the point being discussed. As the course progresses, magnetic fields will not always be included in every illustration. Just know that when the coil is energized with alternating current, it will develop an alternating magnetic field. And when that alternating magnetic field intersects a conductive test material, eddy currents and the secondary magnetic field will be produced, both of which will constantly alternate at a rate depending on the alternating frequency applied to the test coil. When an alternating current is passed through a test coil, an alternating magnetic field is produced through and around the coil. When the test coil is placed near a conductor, i.e., the part being inspected, the coil's alternating magnetic field induces alternating eddy currents into the conductor. The eddy currents generated in the test piece generate their own magnetic field, which opposes the coil's magnetic field that induced the eddy currents into the test piece, as per Lenz's law. The test coil is coupled to the test piece by the coil's magnetic field. It is through the coil's magnetic field that all useful information about the test piece is obtained. Changes in material conductivity, permeability, or geometry will modulate the coil's magnetic field, which will be processed to produce an eddy current signal. Changes to the coil's magnetic field will change test coil impedance, an electrical property that will be covered in the module on test coil attributes. Anytime the flying dot moves around the eddy current instrument screen, test coil impedance is changing for some reason. As the test coil is scanning over the material's surface, the track or path of the flying dot is stored on an oscilloscope-type screen, so the operator can evaluate the signal formation.